Good afternoon. My name is James Storm. I'm working on the Android media team. Today, I'm here to present you a set of new low-level media APIs we published in Android Jellybean release. This set of low-level media APIs allows the Java applications to directly access the low-level decoding and encoding capabilities of the media codecs available on a specific Android device. With this set of new low-level media APIs, as Java developers, you are given much more flexibility and finer granularity control on how your media application behave. Today, my talk is partitioned into two parts. In the first part, I will briefly talk about the existing Android media architecture and the existing high-level media APIs prior to Jellybean release. In the second part, I will focus on my talk on the new low-level media APIs we published in Jellybean release. So let's start off with the brief introduction to the media framework architecture. On Android-powered devices, typically you see many media-related applications, such as camera, music app, gallery, YouTube, movie player, etc. All these applications basically using the same architecture. Each application is partitioned into two separate address spaces. The application process and the media server process. The communication between the application process and the media server process is using the Android remote procedure call or binder call. In the media server process, a set of commonly used media services, such as playback, recording, audio routing, are provided. The media server process then talks to the drivers in the kernel through a hardware abstract layer. For decoding and encoding purpose, the hardware abstraction layer is the OpenMax integration layer. You can find out a detailed reference URL basically at the end of my slides if you want to find out details about OpenMax. So prior to Jellybean release, we already have a set of high-level media APIs. With these high-level media APIs, you are able to write applications quickly. On this slide, I show you a really simple example on how to write a playback or streaming application using a high-level media API, which is the MediaPlayer.java class. At this point, I assume you are pretty familiar with the MediaPlayer.java class. And I will quickly walk through the example on this slide. First, what you need to do is to create a media player object and then set its data source by passing it a URL. The URL can be a local file on your Android device or can be pointing to a media data source that is located on a remote server. So after you configure the media player object, then you can send a prepare message to the media object, which basically will validate the data source, see whether this file format is supported by the parser. And if the parsing succeeded, then you can use the common set of media controls like start, pause, and to control the playback or streaming. You can also jump to a specific time position by calling seek_to if the data source is seekable. So depends on the interaction between user and the application. This process may be iterated like multiple times, And then at the end of a playback session, you want to terminate the playback session by calling stop. Immediately after the termination of the playback session, you want to release all the associated resources with media player object by calling release. So as you can see from this extremely simplified example, you do not need to write too many lines of code. And it provides you a high abstraction level on how you can control a media playback or streaming application. So with this existing high-level media API prior to Jellybean release, we are able to meet the needs of mostly commonly used media application use cases. And we are able to support commonly used file formats. In addition, we are able to support most commonly used streaming format protocol like HTTP, RTSP, HLS. However, as a Power Java developer, you are often given the challenge to do more. So what if you are given a task to write an application to support a file format that is not yet supported by the Android platform? What if you are given a task to write a streaming application to use a streaming protocol that is not yet supported by the Android platform? What if you want to do some image processing on the output of the decoder, and then you send the output for rendering? So what if you want to, after the image processing, you want to send the output to be used as input to an encoder, and then encode it, and then streaming the result out? For this kind of advanced challenges, with the existing high-level media APIs, to be honest, you probably cannot do too much. So that's why we publish a set of new low-level media APIs in Jellybean release to address this set of challenges. So this new set of low-level media APIs mainly consists of three parts. The first part is a file parser. Basically, is a new class called a Media Extractor. It allows you to parse all the currently supported file formats on Android platform. The second part of the new low-level API is the ability to query the capabilities of the media codecs available on an Android device. Why you need this capability is you need to find out what are the available codecs so that you can create the specific media codec to do decoding and encoding directly from your application process. So that's why you need the third part of the API, which is the media codec Java class. So this class provides you the directly access of decoding and the encoding functions of the available media codecs on an Android device. So I will start with the first part, the file parser. Before I want to talk about the details of the APIs in the Media Extractor class, a basic understanding on a general file structure for a typical media data source might help. So a typical media data source consists of one or more elementary streams, which we call tracks. Each track can belong to a specific type, like audio or video or text. So for each specific track, it has one or more sample data associated with it. for each sample data, it can be a decoder-specific data, or it can be the actual compressed access unit of audio frame or video frame. So it can has the data itself, and it also provides information about the media data, such as the timestamp you need to present the data. And usually it also tells you whether, for video purpose, it will also tell you whether the current sample is a sync frame. So with this basic understanding on the file structure of a typical media source, then I will introduce you the first new low-level media API, which is the Media Extractor. So if you look at the Media Extractor, we provide a default constructor for you to create an instance of Media Extractor. And then you can use set data source, which I assume you are pretty familiar with it, a set of set data source methods, similar to what a media player has to configure your data source. So once the data source is configured, you can find out the total number of available tracks from your data source by calling get track count. And then for each individual track count, you can find out detailed format about it by calling get track format. So get track format will return you a object of media format, which is another API we released in Android Jellybean. I'll talk about the media format in the next slide. So in order to use the parser, then you need to select a specific media track to use to read data from. In order to do that, you can call select track. So for instance, a media data source may have multiple audio tracks for different languages. So you want to select a specific language for your application to use. Then you can use a select track. You can also deselect this track so that you won't pass data from this specific media track. You can also to do random seek within the data source by calling seek2, which takes two arguments. First one is the time position you want to seek to. The second argument is basically the seek mode. So for example, if you want to seek to a sync frame, or you want to seek to a time position like that is after but closest to a sync frame. So there are a number of seek modes you can use to affect the behavior, how you seek to inside the data source. If you don't want to do random seek, you just want to move to next sample position, you can just simply call advance, so which will move to the next sample sequentially. So once you reach a specific time position, and then you can read media data or decoder specific information data using read sample data method. So this read sample data method takes two arguments. The first one is the buffer that you want to read the sample data into. The second argument basically is provide an offset that you start to put your data in. It also returns an integer to indicate whether your read is successful or whether it reaches the end of your data source. So if it's a non-negative value, it indicates the read is successful. If it is a negative value, that indicates the read reaches the end of the stream. So for each sample, as I just mentioned in previous slide, you can find a bunch of metadata associated. So one of the important pieces of information is the presentation time. So in order to find the presentation time for that sample, you can call getSampleTime, which will return the presentation time in microseconds. And you can also find out the flags associated with this particular sample, such as whether this sample is a sync frame, whether this sample is a decoder-specific information. If your data source is not a local file source, then you need to do cache the data. So in order to find out how many cached data in the RAM or in the memory, you can use get cached duration to find out how much amount of data actually cached in memory. And you can also use has cache reach end of stream to find out whether cache read, the data cached in memory already reached the end of a stream or not. As I mentioned a little bit earlier, in order to find out details about a specific media track, you need to use a new class called media format. Media format.java class basically encapsulates a set of key value pairs. And in addition to that, it also make available a bunch of setters and getters methods so that you can find out the value or modify the value associated with a given key. For example, if you want to find out a audio track's number of audio channels, you can just provide a key channel count to find out the value about the number of channels. So to give you an example on how this two API works, I will show you two examples. The first example basically show you a typical use of the media extractor API we provided. So first off, you need to create a media extractor instance by calling its default constructor. And then you, just like your media player object, you set its data source. So once its data source is set, and then you can find the total available tracks from that data source by calling getTrackCount. So by iterate through all the available tracks, so you can find out the media track you are interested in, and then you select that specific media track by calling selectTrack. So once you select the particular media track you are interested in, then you are able to read data from that track by calling read sample data. So read sample data basically will read the sample from the given time position into the buffer it provided. If the read sample data returns a negative value, that means you already reached the end of stream. If it is a positive number, that means the read is successful. And in addition to the media data, you can find out its metadata like presentation time, sample time, and flags associated with the sample. And you can decide whether you want to move to the next sample by calling advanced method, or you want to jump to a random time position by calling seek2. So once you are done with this process, can iterate until you reach the end of stream. Once you are done with the media extractor, then you just call release method to release all the resources associated with this object. So how to find out a media track that you are interested in? You need to know the detailed track information. That's why you need to use this media format class. So with this media format class, you can find out the MIME stream for a specific media track. And from the MIME stream, you are able to tell whether this media track is audio or video or any other media type. And if it is audio, you can find out number of channels, sample rate by using the getter methods I mentioned. If it's video, you can use the getter method like get integer and to find out the video resolution. So the use for media format class is really straightforward. I want to emphasize the file parser media extractor class basically supports all the existing formats currently we are supporting on Android platform. However, if you ask to support a file format that is not currently supported, you need to implement your own file parser. So this media extractor basically just provides you an example how you can implement your own media extractor to support a new file format that is not supported. So that's the first part of the low-level media API. Now, let me move on to the second part of the media API. Basically, is the ability to query the capabilities of the media codecs available on an Android device. So we published two new APIs, media codec list and the media codec info. So let me show you how these two API works. For media codec list, it's very simple. There are only two public APIs you can call. The first one is let you find out the total number of available codec count on an Android device. The second method, the first one basically is get codec count method. The second method is get codec info at method, which allows you to find out the detailed capabilities of a specific media codec. So you need to use the new API, media codec info, in order to find out details, capabilities of a media codec. So the media codec info class will tell you what's the codec name for this media codec, whether it is a decoder or an encoder. And you can also find out the number of MIME types that this specific media codec supports. So just for your information, the same media codec may be able to support multiple MIME types. So that's why the get supported types returns an array of string. So basically it tells you all the MIME types it supports. By iterate through the supported types, you are able to find out the capability for a specific MIME type for this given media codec. So you need this inner class called codec capabilities in order to find out the specific capability. So what are the capabilities exposed through this API? Basically, two pieces of information. The first one is a list of color formats that is supported by this codec. The second piece of information basically is a list of profiles and levels supported by this media codec. So to give you an example on how this media codec list and media codec info works, here is a very simple example. Okay, so first you call media codec list dot get codec count to find out all the available codecs on a specific device. So once you have the count, then you can iterate through it by calling get codec info at to find out the detailed capability of a specific media codec. So this method returns you an object of media codec info. So using that info object, you can find out whether this codec is encoder or decoder. And you can find out all the MIME types it supports by calling get supported types. With the array of supported types, then you can iterate through all of them and find out the capability for each MIME type that this media codec can do. So in this particular example, I would like to find out which media codec is capable of decoding a AVC video that is encoded in high profile level 4.0. So how to find out that? And first, you can check the type, see whether the MIME type supported by this media codec is AVC. So basically, just check the type against video/AVC. You can find out whether this media codec is support AVC. So if this video codec is support AVC, then you can find out the capabilities of this media codec. So there are two pieces of information, as I mentioned earlier. One is the list of output color format, and the second one is the list of profiles and levels it exposed. So you can just iterate through the list of profiles and levels exposed by the capability object, and then compare to see whether this media codec is supporting high profile level 4. So the use of this media codec list and the media codec info API is pretty much straightforward. Behind the scene, how this API works. For each Jellybean Android device, we require a registry XML file to be put on the device, which actually tells you all the available media codecs. So on this slide, I show you a simple example of this media codecs.xml file. So in this XML file, you can see there are two lists of media codecs. One list is for encoder. The second list is for decoder. Regardless whether it is a decoder instance or an encoder instance, each media codec entry has a single attribute for name. So this name will tell you the media codec name that you got from media codec info class. So that's the get name method. It will return you the name attribute of the media codec. Any media codec actually is with the same name can support multiple MIME types. So if you have multiple MIME type support for a single media codec, you can have multiple attributes for type. That's why if you look at the media codec info class, it has a method called get supported types, so which will return all the MIME types that you available in this media codec XML file for a specific media codec entry. So that media codec list and media codec info classes addresses the need and what are the available codecs on a specific Android device. So once you know the available codecs, you can use a media codec class to create an instance of that codec to directly access the low-level decoding or encoding capabilities. So how to do that? First, let me show you the API available in this media codec.java class. The first three methods in this class allows you to create a media codec. So a media codec can be created either by the MIME type is support, or if you know the specific name for the media codec, you can just pass the name. You can create a decoder instance or encoder instance this way. Once you have a media codec instance, then you need to configure this media codec for decoding or encoding purpose using config method. This config method requires 4 arguments. The first argument is media format. So this media format, usually you can get the return value from your media extractor. So let me go back a few slides, just show you. See, for example, the get track format returns you the media format objects. So you can just pass that media format object to the config method. So if it's a video track, you want to, if you decide to render the video to a surface, you pass the second argument, the surface argument. If your data source is encrypted, and then you need to provide a MediaCrypto object. The last flags basically indicate to the API whether this is an encoder or decoder instance. So why you need that is because if the instance is created by the third create method, create by codec name, you are not able to tell whether this is for encoding or decoding. So that's why you need a flag to tell. So this config is for decoding purpose or for encoding purpose. The next set of API basically is a standard set of media control. Like you can do start, stop, you can do flash. I haven't listed flash here. I will skip those APIs. Basically, just standard media control API. In the core of media codec API is basically how we pass data back and forth between the media process and the application process and the media server process. We are using array of byte buffers for this purpose. There are 2 array of byte buffers. One used for the input. The second one is used for output. The actual communication between your application process and the media server process actually is not by passing the byte buffers directly. Instead, it passing the index into the array rather than just pass the byte buffer directly. So the next set of APIs basically tells you how to use these buffers. So for input, you have 3 methods. The first one is get input buffers. You need to call this, you only can call this method after you start, after you call start. So this method will tells you the array of byte buffers used for this codec session, either an encoding session or a decoding session. Once you know the array of byte buffers, and then you can find out whether there are any input buffers available for you to use by calling DQ input buffer. This DQ input buffer take an argument with timeout. So if you give a timeout value, negative value, basically you just wait forever until a input buffer is available. Otherwise, you just wait for the specified timeout period. And then if there is no buffer available, it will return a negative integer to indicate its timeout. And there is no input buffer available. So if there is a available input buffer before the timeout period, then it will return a valid byte array index, which basically is a non-negative value. So using this index, and then you can find out the right byte buffer using the input array of byte buffers. So once you find out the right buffer to use, and then you can put valid input data inside this byte buffer. So you can either do some image processing before you put your data in. That's fine. It's up to you. But after you prepare your data and put it into the byte buffer, you can use the next method, QInputBuffer, to send this input buffer to the codec. So this QInputBuffer takes a bunch of arguments. Those are pretty obvious. But I want to talk about the first argument. As you can see, it is an index. It is not the byte buffer. So you need to pass a valid index to this QInputBuffer, which usually you got from the return value of DQInputBuffer. Okay. The next argument basically is offset, basically indicate the starting position of your valid data inside that byte buffer. And size basically is the number of bytes of valid data you put in your byte buffer. The CTS time US argument basically tells you what is the presentation time for this input buffer, and the flags basically are a bunch of associated flags associated with this byte buffer, like whether this is a keyframe, something like that. So similarly, for output buffer, you can find out the array of byte buffers by call getOutputBuffers. Okay. Similarly, we are not using the byte buffer directly between your application and media server process. We are passing the index of the output byte buffer. So in order to find out whether an output buffer is available, you call DQOutputBuffer. The return value will indicate whether you get a valid output buffer. If it is a negative value, there are three cases. Okay, it can be timeout, so indicate there is no buffer available. It can be indicate something like the output format changed. For decoding applications, usually it happens. So you start to decode and you find out the output buffer change. Okay. So the return value, a negative return value from DQOutputBuffer will tell you the output buffer format changed, output format changed. The third negative value can return from DQOutputBuffer is an indication of output buffer itself changed. Okay, so after you receive that return value, you need to call getOutputBuffer method again to get a refresh on the array of output buffers. If DQOutputBuffer return a non-negative value, meaning a valid buffer index, then you can use that for the subsequent call, release output buffer. So before you call release output buffer, you may also do some like image processing on the buffer and using the valid index to find out the correct buffer, byte buffer that hold the data. And you can do some image processing with that data. And then you call this release output buffer. Release output buffer, basically, there are two arguments. The first one, same thing, is an index into the array of byte buffers. The second is a Boolean value, basically indicate whether you want to do rendering for this output buffer. For video, rendering means you want to show the video frame. For audio, meaning you probably want to send to audio sync for decoding purpose. Okay, so for each buffer, for each byte buffer, regardless whether it's input or output, we provide you a set of metadata associated with it. If you look at the DQ output buffer, the first argument is byte buffer info. The buffer info object tells you the metadata associated with a byte buffer. So you can find out information like what's the number of bytes that this buffer holds the valid data, and what are the starting position, like the valid data begin inside this byte buffer. What is the presentation time for this data inside the byte buffer, and also the flags, such as whether this byte buffer hold a sync frame data, or whether this hold the decoder specific information or codec config flag, or whether this actually indicate is end of stream sample. So to show you how to use the Media Codec API, I have 2 slides. The first slide basically shows you a typical use of the low-level Media Codec APIs. So you start off by creating a Media Codec instance by calling one of the 3 create methods. So in this particular case, you create a decoder instance using the supported MIME type. And then you need to configure this codec by calling config method. So the config method basically it needs to know the format that it deals with, this codec deal with. That format can come from your media extractor, okay, if you provide a customized media extractor implementation, or you use the media extractor class we provide for you, and by calling get track format, so that returns the right format for you so that your codec can deal with that specific media track. So once this media codec is configured, you can just start decoding process by calling start. After you calling start, then it is time to get the array of input byte buffers and the array of output buffers, okay? And you can also find out the output format for this media track. Then follow that basically is an iterative process. Basically, you just send input data to the codec to do decoding or encoding, and then you get output from the decoder or encoder. So that's an iterative process in the for loop, as I shown on the slide. So after you are done with the this process, you stop the decoding process, and then you release all the resources associated with this media codec. Let me go to the next slide to show you how to actually send input data to the decoder for decoding, and how to get output data from the decoder. So this slide shows you the details. The first part shows you how to send encode data to the decoder instance. So first you call codec.DQ input buffer, okay? You check its return value. If the return value is non-negative, meaning greater than or equal to 0, then it is a valid buffer index, meaning there is a input buffer available for you to use. So at this point, you know which buffer is available by using the index, which you can find out along with the array of input buffers. And you can do image processing on the input buffer. And once you are done with your image processing, you can call Q input buffer with the right buffer index. And then that API will send the input buffer to the decoder instance for decoding. If the return value is negative, that means probably it's timeout. So you need to retry. Next, I'll show you how to get the output from the decoder. So you call codec.dequeue output buffer with a timeout. Same thing, it returns you an integer value. If it is a non-negative value, meaning you find basically there is a output buffer available, meaning the decoder already generate a output data and it's already stored in one of the output buffers. So how to find out that byte buffer? You use the return value from dequeue output buffer, use that as an index into the array of output byte buffers. And of course, you can also decide to do some image processing with it. It's up to you. After you're done with it, and then you can release this output buffer back to the output buffer array pool. If the return value from dequeue output buffer is negative, there are 3 cases I mentioned. Okay, the slides only show 2 cases. So the first case is timeout. Basically, you can check whether it's timeout. If it's timeout, you can retry and until you find a output buffer available. Otherwise, if the return value, if info output buffers changed, that means the buffer size or number of buffers may change. So you need to get a refresh on the array of byte buffers for output. So you call get output buffers for that purpose. For the third case, if the return value is info underscore output underscore format changed, that means the decoder will find out the codec format basically changed, or the subsequent sample output will conform to the new format. So in order to find out the new output format, you can use get output format for that purpose. So to wrap up the API for media codec, I want to mention a couple of things more. First, although the example is given using a decoder instance, most of the APIs in this media codec class basically is the same for encoder instance and decoder instance, so that you do not need to learn two sets of different APIs. Second thing I want to point out is if you are using media codec API, it is up to the application to do the audio and video synchronization, because we return the buffer info to tell you what's the presentation time. Now the application has the information to do proper audio and video synchronization. Well, with the release of this low-level media codec API, now it is up to you to write more sophisticated media applications to your imagination. Before I want to open the floor for questions from the audience, I want to thanks Andres in particular for developing the low-level media APIs for Jellybean release. Also, I want to point out if you want to find out more information about OpenMax spec, you can use that URL on the Q&A slide. Now, let me open the floor for questions from the audience, if there is any questions. Thank you.
Hi. Thank you for your presentation. So 2 questions. One is the actual decoding and encoding happening inside of the media server process still?
Yes, that's true.
Okay. And so in terms of battery consumption, if you were to write a media player application using these APIs versus a natively written one, how would they compare?
Yeah, that's a really good question. So we did some experiment. Although our test app is not instrumented, and the findings basically, the initial findings using the Media Codec API, we find out the total power consumption for the application basically is roughly 10 to 20 milliamps above what we have using media player class.
Okay, thank you.
So a little bit more, but I think it's acceptable.
Thank you.
Sure, thanks.
Thank you for the presentation. I have a question about those low-level codec APIs. So does that mean that I can write the application to do the real-time video chat with those APIs? My understanding is that those codec will enable leveraging the hardware capability through OpenMax protocol, right?
That's true. The Media Codec API actually allows you to access the low-level decoding, encoding capabilities, regardless whether the decoder is a software decoder or is a hardware decoder, or regardless whether the encoder is a software encoder or hardware accelerated encoder. So you can leverage the hardware accelerated media codecs.
And my understanding is that prior to the Jellybean, those are not exposed, right? At least for encoding. For the hardware
That's
capability.
true. That's why I said this is a new set of low-level media APIs only available in Jellybean and after.
Okay. Thank you for the answer.
Thank you.
I have two questions. One, is there a X264 hardware-based encoder that goes with the 4.1 that is accessible through the low-level APIs?
To answer your question, yes. For example, the current device, for example, Nakasi and Prime, all provide you the hardware accelerated AVC decoder, which are able to decode AVC high-profile level 4 videos. Okay. So really it depends on the device capability. Okay. So if you have a low-end device, you may not be able to have the hardware to do that. So that's why you need that capability query APIs to find out.
And my second question, is there an RTSP streaming component that could integrate with the encoders so that work with the new media APIs?
RTSP streaming
Server,
yeah. Server we do not have, but we have a client implementation.
Okay, thank you.
Yeah. Thanks.
Two questions. First of all, with the release of Jellybean, are you adding any extra codecs that kind of implement these APIs that would serve as good examples?
Your question basically asks, say, whether we have additional media codecs to support the
added in Jellybean versus
added in Jellybean. Well, this is really depends on the device you have, but the commonly available codecs are basically like for video. You have AVC decoder, AVC encoder. You have MPEG-4 video encoder decoder. You have H.263 encoder decoder. You would expect it to have on a commonly available Android device. For audio, you have a bunch of formats like to support decoder for MP3. For encoder, you have AAC, AMR, narrowband, wideband. So all those are supported.
Okay. Second, you kind of mentioned the MediaCrypto, I believe it was, for the actual like DRM, I would assume, production. Can you go into a little more detail on what would be involved in using that in your app?
Yeah, that's unfortunately out of the scope of this presentation, and which is another basically a talk itself. But basically, you can we publish a new API called the MediaCrypto class. you can do decoding of encrypted content. So currently, we implement this and verified with wide-wide DRM, wide-wide encrypted content.
Okay.
Does that answer your question? Yeah, otherwise, like, it's another long talk, basically, about MediaCrypto API. So once the API is published, you can look at it. It's pretty simple, also.
The APIs are going to be
For MediaCrypto.
When is the actual documentation of that going to be totally available?
It's going to be released with the SDK.
Okay.
Right.
Great, thanks.
Okay, thank you.
So you mentioned in the configuration that it uses Surface. What does it use that for, that value?
Okay. The second argument for configure method is the surface. So if you want to render your movie, your video output, for example, then you want to pass a surface so that it can render that video output. That's for that purpose.
Okay, and how does that work with the syncing of the audio? Would you render the movie and then have another thread that's parsing your audio?
Yeah, then it's up to the application. Basically, you probably need to write multiple threads. One thread is handling the video, the other thread is handling the audio. But it's up to the application to do that.
Okay, so you just pass the surface in for us to use?
Yes, we just pass the surface as the video sync.
All right, thank you.
Yeah, thank you.
Hi. In Ice Cream Sandwich, you released a new low-level streaming API. Will Jellybean build upon or replace that one?
Sorry, let me turn this one off. Sorry, what's your question again?
In Ice Cream Sandwich, you released the new OMX AL streaming low-level library. Will Jellybean replace or build upon that?
Well, it's used for different purpose, basically. It's used for different purpose. And I think from Jellybean and on, we should focus on Media Codec API.
Will the ICS one still be supported then?
It will be still supported.
Okay. And then you mentioned MediaCrypto. Is there a way to protect the decrypted yet still encoded data using MediaCodec then? Or
yes.
MediaCrypto?
For encrypted content, actually, you are not able to actually accessing the output byte buffer. So it's opaque data, basically, to the application process. So if you have hardware-assisted protection for your video path, then the output buffer actually is hardware protected.
Does it just support Widevine, or do custom DRM support it too then?
Currently, we only verify the implementation with Widevine, but I can imagine it also able to work with other schemes.
Okay, thank you.
Thanks.
My first question is there any constraint for threading access of these buffers? Say, usually we will use different thread for collect data and maybe another to call a codec. So is there any constraint on thread part for accessing the input buffer or output buffer?
Sorry, can you rephrase?
Oh, let me make it simple. When I access the input buffer and output buffer, can I use a standalone thread? Is there any constraint for it?
No, it shouldn't be. As long as you have a valid input buffer or output buffer, you can use it for your own purpose.
Okay. My second question is, you mentioned about the extractor decoder. Is there any way to get the hardware color conversion, like YUV to RGB?
No, there is no API we publish in Jellybean for that purpose,
Okay.
for color conversion.
Okay, and you mentioned the codec information can tell the profile and the level supported. And
Yes.
is there any way to know the profile or level of the media source?
The profile and the levels for the media source. No, currently we are not supporting that. So as an application developer, you need to know the source, basically.
Maybe not.
If you do not, then the Codec API will indicate like it's not able to handle if the codec is not available to handle.
I haven't read the document. Is there any error callback since?
There's, well, for example, the set data source and get track count may, you may not get the right number if the file format is not support, for example.
Say if the audio is support, the video is not support, so maybe the check account will be 1 instead of 2?
Yes.
Okay. And my last minor question is, in your code showing in the screen, you use 2 equal to compare the codec MIME type. Is it safe?
2 equal, sorry.
2 equal signal, instead of call a string equals 2.
Yeah, that probably my, yeah, but basically just compare the MIME type against the supported, MIME type. So.
Okay, thank you.
Sure.
Hello, you haven't mentioned the Android NDK at all. So are the same set of API changes also available from the native side, like from the NDK side?
No.
No?
This is all Java API.
Okay, and have there been any changes to the NDK exposed APIs at all for Jellybean?
Not as far as I know, yeah. This is just Java APIs, not related to NDK.
From the looks of your sample code, it's really just a thin wrapper around some native code, like most of the classes?
Yes, those will be available at the native layer, but it's not part of NDK.
So you cannot actually call these from...
No, we are not recommend you to call directly into the native code.
Because some like audio APIs are actually exposed in the NDK. Right?
Yeah, if it's exposed in the NDK, you have the guarantee like we will maintain it. But if it's not part of the NDK, then we may change it. So that
if you want to write some really low latency code, for example, and you have like you're calling native code anyway, so it kind of would make sense to actually expose these codecs natively. But yeah.
Yeah, but for Jellybean release, we are not exposing that.
Thank you.
Yeah, thanks.
Hi. So you mentioned about we need to do the YUV to RGB conversion. So can the surface be backed by a surface texture? In that case, will we get something as a YUV texture, and we can use a GL to do the color conversion?
Sorry, I haven't mentioned that, but it's up to you to do the image processing. Not necessarily you do color conversion.
Okay.
Okay. So the Media API basically gives you the raw data, like the output of uncompressed video frame, for example. You can do image processing on it. And
it is in what format? Is it RGB?
Well, the format will tell you, basically you can call get output format. You can find out what's the format there.
And it is expected to be in an RGB format and not an intermediate YUV format, is it? Because
no, it's a decoder output. So it could be, mostly it is YUV output format.
So that means we need to do the color conversion.
Well, it depends on how you do your image processing, yes.
So if you don't do image processing and we just say Boolean render to be true, the underlying platform will do the color conversion and render it to the surface?
Yes.
And are these buffers getting copied in any way? Like the decoder could use the decoder resources to push the decoded buffers. Is it getting copied from the GPU memory to CPU memory?
Well, we try to avoid mem copies, as much as we can. And as far as I know, there is no copy at all at the media level. And the only traffic communication added for this media API is the indices of this input buffer and output buffer arrays. Basically, that's the added communication traffic between the application and the media server process.
But then if the decoder is using GPU memory, and if it has to be passed as a byte array into Java, wouldn't it have to be a non-GPU memory for the application to do any kind of post-processing?
Well, the byte buffer array is basically just a wraparound of the native buffers. It may not necessarily say a specific format for that.
So it could be textures too?
It could be.
Okay. And how do we know if it's a texture or not?
You don't know at this point. There is no API tells you about it.
But if we have to do post-processing, we should know how it is represented inside the byte buffer, right, in order to read those data?
Well, the data itself actually is arranged in a way that you can access it by basically find out the output, the YUV format, and the size of it.
I see. And the encoded data is passed as like elementary streams?
Sorry, I think we are running out of time, and we can take this offline. All right? Okay. Thank you.